Hello and welcome to the parameter learning chapter. I will start with section 1, maximum likelihood estimation. Back to our COVID problem, we have a data set of 1,000 samples. We saw that if you're given a factorization of the joint probability distribution, how you can draw this Bayesian network structure. We also saw how to read conditional independencies from this graph. And also, if you're given the CPDs, how to calculate inquiries. But we didn't discuss how we can actually learn or estimate the CPDs. And that's the question here. So assume that you have learned or you're given a Bayesian network structure or correspondingly, a factorization of the distribution. The question is, how can I find the CPDs corresponding to each of these nodes here? And this task is called parameter learning. But to elaborate, I will start with a simple example, the coin tossing example. The task is to determine the fairness of a coin after tossing it 10 times. Possible outcomes, of course, are head and tail, and the probability distribution parameterization can be done with a single parameter theta. So probability of heads theta, tail 1 minus theta. Of course, to learn or estimate the parameter, we need data. Here, we were asked to do it 10 times, so I'm giving you the data set 10 times and the variable of interest, heads or tail. Here we see the observations. Okay, so how can we do it? I recall the likelihood function. The likelihood function is the joint probability distribution of observed data, given that it is generated by a specific model with parameters theta. And this is how it's denoted. P of data given theta. So you see, I'm incorporating the parameter theta into the probabilities. So basically what this likelihood function means, it is determining how likely the data is to be generated by the model with parameter theta. So in the coin example, whatever value we pick with theta, we want to see how likely it was that we observed that table with that parameter. Now, to emphasize the fact that the likelihood is a function of the parameters, it's often also denoted by L in this form, L of theta given D. Okay, but just note that you shouldn't confuse it with the actual probability. Both of them, regardless of the notation, it's the probability of data given the parameters. That's the likelihood. Now, what can we do with it? Well, naturally, we would like to maximize the parameter that the likelihood and find which parameter maximizes it. The parameter that maximizes the likelihood are known as the maximum likelihood estimate. Theta star, our estimate, is the argmax of the likelihood. Back to our example. First, we need to make a few assumptions. Assumption 1, the coin tosses are independent. I'm writing in gray here, given the parameter. Now, often this is not implicitly mentioned. We just assume that each toss, each sampling of the data is independent of the other ones. But here, now that we're putting in theta into our probabilities, we need to do it more carefully. So P of tail, for example, appearing in the first instance, which is P of x1 being equal to tail, given that the parameter, the probability of having head, for example, is theta, it will be 1 minus theta. What about having head appearing in the second instance? Well, of course, I'm not conditioning it on anything, so it's theta this time, it's a head. But what if I condition it? So head appearing at the second instance, given that tail appeared at the first instance. P of x2 equal to h, x1 equal to t, and of course I have my theta parameter here. Well, this is the same as probability of head given theta, or basically theta. It doesn't matter if I tell you that, look, in the previous toss you had a tail. What does that change the probability of having head this time or having tail this time? No, it doesn't affect that. This is the independence assumption of the coin tosses or the data instances. Assumption 2, the coin tosses are identically distributed. And that means that the probability of having head at instance 2 is the same as having head at instance 3 and at instance 5 and so on, everywhere else. Theta, if once we know that the parameter of our model is theta, whatever it is, then these are all the same. It doesn't change, for example, over time. And the same with the other one, which will be equal to 1 minus theta, the tail. So the likelihood function equals probability of data given theta, which I can calculate instance by instance. The first instance was tail, so I put 1 minus theta. The second one head, I put theta. Third head, theta, and all the way until I get all the 10 instances, and that will result in theta to the power of 6, 1 minus theta to the power of 4. I want to find the maximum likelihood, the parameter theta that maximizes this. So I just need to calculate the derivative and let it equal to 0, which I did here, and that results in 0.6. So the theta, the maximum likelihood estimate, equals to 0.6. Our best guess for probability of having head, which was our parameter theta, that is 0.6. Okay? And as an exercise, you're asked to show that in the general case, the maximum likelihood estimate simply equals to the number of heads that appears here divided by the total number of instances. N of h plus n of t, and n is the number of appearance. So let's check if it's true in this case. I have 10 in total. How many heads do I have? 1, 2, 3, 4, 5, 6. Yes, it's correct. 6 divided by 10, which is 60% here. Great, now we know how to find the MLE of the coin tossing problem, but how can we do the same thing for the Bayesian network? Well, let's consider a simple Bayesian network, the COVID mask problem. Here we have written the joint probability distribution using the chain rule in factorization of two terms. So first thing is to parameterize the Bayesian network, the CPDs. So for mask, we know that it takes two values only, so we need just one parameter, they add up to 1. And for COVID, we know that it also takes two values, so condition on M, overall we need two values, because each row adds up to 1, two parameters. So we'll have all these parameters written like this. So the general parameters will be theta M0, theta M1, C0 condition on M0, and so on, whereas indeed we only, out of each pair here, we need only one of them. Okay, so we want to estimate them based on this table of data. So how can we do that? The data here is D, and we can write it down as M of T and CT for all the 12 instances. And the task is to find the MLE from the data set. So how can we do it? Let's just write down the likelihood probability of data given theta, which is basically in the expanded form all the instances, 12 instances, condition on theta. And well, this, if we write it in the compact form and using the independencies between the instances, recall how we described that each time you toss a coin, it's independent from your previous toss. Same story here, the instances are independent of each other, so I can just factorize them into the 12 instances. And then using the Bayesian network factorization rule, or just the chain rule in this case, I can factorize it into these two terms. So if you just ignore theta for a moment, then you will see it's just writing the joint probability of M and C as P of M times P of C condition on M. Okay? So nothing new there, and obviously this multiplication, I can write it down as the multiplication of these two terms. So first multiplying the first term, all the 12 instances, and then the second. So how can I calculate these ones? Well, this is 12 instances for P of M condition on theta. How can I calculate that? This is the same as the coin tossing problem. I just need to count how many times M was 0 here, how many times it was 1. So theta M0 to the power of the number of times it was 0, and theta M1 to the power of times it was 1. What about this other one? Well, it's the same story. It's asking like P of C condition on M for each instance. So the first one, for example, is C equal to 1, condition on M equal to 0, and we know that this conditioning is written exactly here. We just parameterize it, M0 condition on C0 or C1 and so on. So I just need to put this parameter for, here I have C1, M0, so this parameter for instance 1, and then for instance 2, it's the opposite, this one, and so on. So I just count how many times, for example, 1 and 0 appear, and then for that many times I will have this parameter theta C1 condition on M0. So if you think about it, it will just appear as the power theta C0 condition on M0 to the power of number of times C0 and M0 appear together in this data set, and so on. Now in this particular case, I will have number of times M0 appeared. It's 1, 2, 3, 4, so I just put 4 here. For M1, same story, I will have 8 times, they add up to 12, so I know this will be 8. And what about the n of C0 and M0? Well, I can also just count how many times the two appeared. It's exactly 1. I put 1 there, and I can calculate the remaining of them as follows. So I will have my likelihood function in this form, and as we discussed, these two parameters add up to 1. So I just can replace them with the other parameter, theta M0, 1 minus theta M0 to the power of 8. Theta C0 condition on M0, the other one, it used to be C1 condition on M0, I'll just replace it with 1 minus that. Now that I have this, I can take the derivative. If I do all the calculations, so for the first one, I just want to calculate the derivative with respect to M0. So I can ignore just all these other terms. Okay, I only need to be concerned with these first two, and if I do that, I will get my MLE for M0 as 4 divided by 12, and obviously the other one will be 1 minus this, which will be 8 over 12. And then I can do it for C0 condition on M0, same story. I do all the math, and then once I get it, I can get the other one, which is just 1 minus that term, and so on for the last parameters. So after doing all this, I get the maximum likelihood estimate for my COVID mask problem, which are the results here that you see. Great. Now, in general, if I just consider this COVID mask problem, but for the general case where I have n of M0 and n of M1, if I do the calculations, the derivatives, I will see that these terms will be factorized, and I will get my MLE equal to the number of times that the mask appeared to be 0 divided by n. So similar to the coin tossing problem, theta star of M0 is equal to n of M0 divided by n. And obviously the other one will be just 1 minus this. And the same story for the conditionings. So theta star of C0 condition on M0, it's the total number of times C0 and M0 appeared in the data set divided by the total number of times M0 appeared. It's quite similar to the definition of conditional probabilities. P of C0 condition on M0, it's P of C0 and M0 divided by M0. And we can get the other one similarly. So what did we observe? Well, the remarkable observation is that the optimal parameters based on the MLE method for this Bayesian network at least was, they were obtained by enumerating over the data set. That's simple, just we counted. Does this observation hold in general? Let's see. Well, to formalize it, given a Bayesian network with the structure G and joint distribution P over random variables x1 to xn, by parameter learning, we mean to estimate the CPDs known as the parameters and denoted by theta xi condition on the parents equal to this probability. How? By using a data set D with instances xi1 to xin. And of course, recall that the joint probability distribution can be factorized according to the Bayesian network. Now note that here, I'm parameterizing each probability of a node, each realization of a node condition on each realization of the parents. So that's why we're using small letter x here, small letter for the parents. But we can group them to make the notation more compact in this form. So if I consider the vector of all realizations of xi and parents of xi, put them in a vector, and that's why we're using this bold theta, bold math, then I will have this more compact notation. So we can think of here having C0, for example, condition on M0, condition on M1, C1 condition on M0, condition on M1. Here I will just have capital letters C and D. Okay? And then I will put all of these conditional parameters for each node 1 to n and put them all into this parameter theta. Great. So after doing this parameterization, now I can calculate the likelihood, probability of data condition on the parameters. This, by using those assumptions that we made, conditional, the independencies of the data instances can be written as t equal to 1 to n, for t standing for each instance. And using the Bayesian decomposition, I can write it down as each probability of each node xi condition on its parent. And of course, I will have theta here. We saw this in the small examples. Okay, so here we can see that I can just put the parenthesis on this term, nothing special I'm doing here, and I'm just replacing the place of these two, so putting inside the parentheses the multiplications over the instances, and I want to call this term local likelihood. I will get there. Just before that, note that here, this term, the probability of xi condition on parents of xi, this doesn't depend on all of these thetas. It only depends on its corresponding theta, xi condition on parents of xi. So with that being said, I have the local likelihood defined as xi condition on its parent at all the instances being multiplied, t1 to n, with this parameter. Okay, and this, we can further simplify it. So what will this be? This is basically probability of xi condition on parents of xi, condition on this parameter. This is basically the parameter xi condition on parents of xi. How many times does it appear? Well, the number of times that both of these xi and the parent appears. Okay. So if I have this local likelihood function, then I have this global one, and here I have this local, so I can just write down that the total likelihood can be written as the multiplication of the local ones for each variable. This is great. This is a great property, because now the global decomposition that we saw here allows us to calculate the MLE for this total likelihood by doing it for each of these local likelihoods. So if I want to take the partial derivative of L condition on any of these parameters, I don't need to do it on the whole likelihood. I just need to focus on this local likelihood corresponding to that parameter, which you can guess how easy it makes all the calculations. Similar to what we observed for the COVID and the coin toss problem, we can see that then we have this proposition that the MLE of the CPD parameter, theta xi condition on parents of xi, which is basically the CPD in the Bayesian network, this is obtained by this formula. So the optimal one is equal to the number of times both of them, the node and its parent, appear in the data set divided by the times that the parent appears. And we said that this looks like the definition of a conditional probability. Now I want to quote here from Professor Ross Greiner that this is embarrassingly simple. The MLE for the Bayesian networks, to get the parameters, the only thing we need to do is just to count. Count how many times each node with the parents are appearing and how many times the parent is appearing. Extremely simple, extremely fast to be implemented and to be calculated. Okay, great. Getting back to our first problem, see it in practice, the COVID example. You're given this network and you're asked to find the CPDs. Well, let's just focus on a small case here, the mass social distancing COVID of this larger network. So how to find the CPD corresponding to COVID when the person wears a mask but does not keep social distancing. So that is basically theta of C condition on M1 and D0. Okay, so I want to estimate both C0 and C1. That's why I have this capital C. Now, of course, I need data. So imagine that I have this data set where I'm extracting it from this 1,000 instances. I need to focus on those where M is equal to 1. So imagine that if I find them, I have only 12 instances where M is equal to 1. Okay, now out of these, you could also do it with respect to D0. But out of these, now using the formula, I just need to count. So we have these 12, 6 of which have D equal to 0. So I already know my denominator. And how many also have C1? Well, there are just 2 of them. So the number is 2 divided by 6, which is 0.33, and that's it. I can do the same for the other CPDs, and I will get all the parameters. So in particular, the C0, the not having COVID condition on this will be 1 minus this, and then I have all the parameters for this term. Great. Let's just have a look at a special case. What if in the data set, those individuals who reported those who wore a mask, M equal to 1, they all kept social distancing as well. So imagine that in my data set, I don't have any instance with M equal to 1 and D equal to 0. Okay, so all these terms are 0. Now, how can I calculate and find my MLE optimal theta that I did in the previous slide using this formula? The denominator is 0. I can no longer use this formula. Here we can interpret the situation as we don't see the case of M equal to 1, D equal to 0 in the data set. So to us, there is no information about this situation, and therefore contracting or not contracting COVID, we wanted to know what is the situation with C, they're equal. We can consider them to be both equal to 50%. Now, if you think about this, this is as if we had added one instance for c equal to 0, m equal to 1, and d equal to 0, so the opposite of this case, and one for exactly this case to the data set. Now, then if I use the above formula, I will get the same result. It will be 1 divided by 2, okay, so which is 0.5. This interesting observation, we will revisit it later in sections on missing value. Thank you.